Here is an introduction to the computer program called the Nominal Moment Calculator. And this is a computer program that can calculate the nominal moment capacity of a concrete beam. And so what you want to do is, of course, you can go up here to the input and you can put in some project information if you want to, but it's not necessary. It's only if you want to. You can also go up here to geometry input and you can put in various layers of steel in the cross section of the beam. Now I'm going to do an example and I'm just going to put 2 number 9 bars, so that's going to be equal to 2 square inches total for those 2 number 9 bars, and I'm going to put that at let's say it's at 15.5 inches, and I'm going to leave this up here saying that I only have 1 layer of steel and I have a height for my beam of 18 inches and a width of 12 inches, but I could click over here and change this to 14 if I wanted to inches. And then when I'm done, I can just click done, and you'll see that it has updated this cross section to be the 18 tall, the 14 inches wide, the 2 square inches of steel, and the depth of 15.5 inches. You'll also notice that up here it has calculated the phi-mn value, and it has done so in kip inches and also kip feet. Over here we can see the output. It repeats some of the user input that we put in, and then it also provides a summary of some of the results and calculations. It can calculate the phi value and the phi-mn values down here. It also calculates that value of C that we learned about in one of our previous videos, and it is basically the region of concrete that is in compression. This portion down here below this distance C is the portion of the beam that is cracked, and so it is not providing any tensile resistance. It's as if only this steel bar down here is providing the tensile resistance, and in fact that is the thing that is providing the tensile resistance. And so anyway, that is a way to input some information and get the nominal factored moment resistance for this reinforced concrete beam. Now we could go back up into input and we could also change our material properties. Now the steel properties oftentimes will just remain as they are in their default values. You of course could change to 40 KSI steel if you wanted to. You could also change your compressive strength for concrete. Let's put it up at 4 KSI. And our epsilon U value is 0.003. There's probably no reason to change this value when you're doing reinforced concrete. But here we've changed our concrete strength, and so then we can click done, and it revises that value and it recalculates what phi-mn is, and it also revises our picture of the beam cross section. There are some other things that we can do. We can go up to geometry and we can add another layer of steel. Let's do that. So we're going to say we're going to have 2 layers of steel. We're going to add another 2 square inches, and over here let's put that layer in at 13 inches. And then click done. Now we can see the new cross section. Those 2 bars are represented by just a single bar, but you can see the summary of information over here. Now it showed their location in the cross section. This distance to the neutral axis of the beam is denoted by C, and it has been adjusted also because we added more steel. The phi mn value has also been updated. Right here we can see the values also, the output of results. We can see in this particular case that phi is equal to 0.886. This actually is an indication that our steel strain is less than 0.005, and that's why it's starting to drop below 0.9. Now, I don't recommend that we design cross sections with phi less than 0.9. So this would mean that this cross section has too much steel, and the solution to that problem is probably a couple of things. One, you'd want to reduce your amount of steel. Secondly, what you could do is increase the depth of your beam, or you might increase the width of the beam. Those things may help you so that you don't have a steel strain below 0.005. Another thing that you could do is go up to the input, go back to geometry, and you can come over here and enable a T-beam option. This is the situation where your beam has been cast as part of a slab, and so that slab is actually going to act like flanges for the beam. So we're going to take a look at that. We can enable this option by clicking this button, and you can see now it shows a depiction of the geometry of a T-beam type cross section. The thickness of that slab, or the thickness of the flange, is denoted by H sub F, and the width of that T-beam at the top, at the flanges, is denoted by B sub EFF, which stands for B effective. So we can put in here maybe that we have a 4-inch slab, and we can also say that our effective width, which there are rules for calculating what your effective width is in the code, and I'm not going to present that information just now, but you can certainly look that up in the code. But in our case here, let's just suppose that our effective width came out as 40 inches. So we'll put that in, and then we will click Done. Now it is calculating the cross-section nominal moment resistance by assuming this type of geometry. And you can see that this little graphic has changed, and also phi mn values up here have been recalculated. Now you'll notice there's a little pn value up here. We can go to input and look at that. It has to do with this applied load, but I'm going to tell you for right now, just don't use that and ignore that option. It is also possible to save your input and also reopen saved input files. You can try that out and see how it works. The other thing is you can come over here and there is a help option. There is some explanation over here for a variety of the things that are found in this program. And of course there's a disclaimer about being properly qualified to use this software. Even though this software says that it is for ACI 318-08, it is still appropriate to use the calculations that are provided here for ACI 318-14. Of course there's also the About option, and it just indicates that who it was written by and the name of this program. So there you go. I hope that's helpful to you as you check out various beam designs that you might come up with. Your calculations should match what this calculator will calculate. And so if you've done a beam design and you want to check whether or not phi mn that you calculated is correct, you can run this program, input the information, and check out the results.